9.2b, really perception and vision is all about going back to one of those original forms of psychology, one of the original disciplines, gestalt psychology, and it's this idea. It really is perception, right? Perception in its psych form. So big idea, whole is greater than the sum of its parts, is that we don't just perceive details, right? We are not bottom-up processors. Inherently, we are top-down processors. We base everything based on previous information, and we tend to look at all of this as parallel processing, right? We look at all the things together and we smash it all into one. Oftentimes this is good. Oftentimes it can cause problems. It causes us to miss details, and we get all these kind of other stuff messed up. So first concept to recognize of Gestalt is a Figureground, and it's that we rapidly differentiate between what is in the foreground and in the background. Think about when you're like reading any information, right? Or even this PowerPoint slide, right? Like looking at this presentation slide, what is the ground or the background? Right. In this case, you see the blue or this like dark blue color as the back, and the white jumps off the screen at you. Right. This is the figure. You're looking at this. You're not looking at the blue. Right. You're not seeing this interesting like shape of blue popping out at you. You're seeing these white popping off. And if we had changed it to white with the blue words, we do the same thing. That happens immediately. Right, we have these figure ground perceptions pretty much instantaneously. Our brain does that for us. So first thing that our brain does in perceiving information is it recognizes, what should I be focusing on? What is the information that is important? What's the figure compared to what's the ground? We don't so much look at the background. We kind of zone it out. We push it to the background because it's not as important to us. Right, look at this image here. Right, like we pretty quickly are like we're confused by it because it doesn't I think it quickly comes to mind for me, at least when I looked at it, that the black is the background, and we see these like columns or chest-looking pieces here. If we look at it a little bit more, right, you can kind of flip it as you had with the old lady, young lady. You recognize that these like black figures are people, right? Like the what was the background, we can now kind of see as a foreground if we change our perception a little bit. Right? Same thing here. What's the foreground? What's the background? Are the faces what you see first, or is the goblet what you see first? Right? Are the faces the foreground, or are they the background? Trying to figure those things out. Other things that we do is we group, right? Our brain automatically puts stuff together. We don't bottom up process. We do several things. So like proximity, when you look at this, your brain likely didn't see 6 different lines, right? It probably saw 3 sets of 2 lines. Because these are a little bit closer together than these, we group this, and this, like set of 2, set of 2, set of 2. Here, what do you see, right? Do you see 2 U's, 2 humps, a couple different lines? Like you don't notice all these different shapes. You notice a straight line and a curvy line. Right? We see 2 things. We see that smooth, continuous pattern rather than chunked. Right? We don't see a shape here, a shape here, a shape here, a shape here. We just automatically put that together into 2 things. Same thing with closure. We often fill in gaps to create a whole. Right, so like look at the difference between these 2. Well, likely you can probably see the triangle in each, but in this one, like our brain will almost always build a triangle without that closed off, because that's just like what makes sense to us. Whereas here, you close this off, and these are much more like a whole. Right, when you actually physically close off these circles, now we see it as 3 different circles compared to like this triangle shape, as much as we did in the first one. You can see lots of different examples of this. Like none of these, if you bottom up process, what do you see? Here you see 18 white dots, 18 black dots, but it's oftentimes we see this as like one big square, or 3 lines of white, 3 lines of black. Same thing here, right? Like this is a checkerboard. Right, we see this as like the UNC plaid almost, but why? Right, we do that. We just automatically put these dots together. There's no reason for us to think these dots go together, other than it's in our experience that's what they are. This is a star. Is it though, or is it 5 Pac-Mans converging on a hapless little Winky right here? Right, so we put stuff together. We have that automatic form perception. We group stuff based on that. Depth perception, another biggie. And this is something that's more or less innate, right? Like you can tell the difference and like how far away things are. This is true for us, but it's true for just about every animal as well. It's been tested in babies. They did this with visual cliff, psychologist Gibson and Walk, where they built out this like white plexiglass see-through area with like a visual trick underneath it, so the babies couldn't really tell. They couldn't tell that it was glass. And so when they were up on the top, the mother would stand on the other side and say, "Hey, crawl to me," and babies wouldn't do it. Like almost every baby just like rejected the idea. And the same thing works with animals, right? Like even birds, they can like immediately just like when they egg, pop out of the egg, they'll like look over. They can look over the side and be like, "No." I can tell. They can recognize that that is far and that far is bad. Kind of evolutionarily, this makes sense. And so we're born with like a slight innate fear of heights, but then our experiences change that, right? So everyone has at least a little bit caution around heights and the recognition that like this could be bad and I don't want to try this. But we can experience can shape that to where we don't have much of a fear of heights or we have more of a fear of heights. And we get depth perception from binocular or monocular clues. Binocular clues, bi meaning two. Think of the two eyes. Right? We have to recognize. We have to use both of our eyes to get some cues. So think about that, like two pins. Right? Take two pins if you want an example of this, and basically what your brain is going to be doing is comparing the difference between each different eye. Right, so we're getting cues from both the left and the right eye. So try to hold it out in front of you, and you've got like the ballpoint pin, the tip of each. You're going to try to move them together and see if you can get them to tap. Perfect. It's going to get a lot harder if you don't have those binocular cues, right? You think you can probably do this, but like now move them out, close one eye, right? So I've got my left eye closed. I've now got just my right eye. I'm going to move these together and I missed, right? Let's try this again. Missed, right? It's a lot harder, right? So try it on your own. Again, you got nothing else to do. Might as well. Let's do some science. And this is that retinal disparity. We're looking at the difference between the two. And again, if you hold that up, you can switch back and forth between the two eyes, and you can see the difference between those. It's going to shift a little bit, especially as the closer it gets to us. Create your fun little finger sausage. I remember as a kid, you're like, this was freaking hilarious. When you create that third finger, as you move it out, eventually it goes away. Right, that retinal disparity, the comparison. So the closer things are, the more we need these binocular cues. Compare that to monocular clues, which are further away, right? Like if you look at something way off in the distance, right now I'm like looking out the window at the like telephone pole outside. I can flip my eyes back and forth, and it doesn't look any different, right? I can't really tell. So in that case, we really only rely on each individual eye. It doesn't make any difference, and we use that that one eye, to be able to differentiate it. We can use both eyes independently or on their own. Monocular clues means we don't need both eyes to be able to tell the difference. Our brain can recognize here in this bottom right that this balloon, because of its size, it's larger. And maybe how much it's moving, we could tell as well, figure out how close it is compared to us. So our monocular clues take in all of these things, and then they tell us where they are. Right? So we take in height, size, motion, shadowing, anything like that, and then we recognize and think about, where is this, right? In comparison, where is this, right? Look at like the shadowing here, right? Like you recognize that like this one is above these two because it's like, it's casting a shadow. It's a slightly dimmer shadow than this one. Motion perception, we do this pretty naturally, right? Recognizing things getting closer, further away, but we can do that, and it's like basically change over time. We use this in some ways to help with our depth perception, right? A larger object is going to move more slowly, and so that tells us where it is in position with everything else. And vocab term to recognize that phi phenomenon. This is that idea that like just by adjacent lights blinking on or off, that you can create motion, and this is pretty common in movies. They do this as a way to, as a cheap way to show movement, is like make flashes at different points. So like pay attention to this upper right, you can see the 5 phenomenon, right? All that's happening is these are just kind of blinking, right? Is that white ball moving around? No, right? These different things are just moving. There is no actual movement, but our brain tells us that white is moving, right? So look at the screen as we kind of toggle through this. It's not moving. It's just different things are jumping around. And if we did this randomly, right? So if we just like did ones that you wouldn't notice it. So 5 phenomenon that you notice it, just the blinking of lights creates us. So we see motion. Our brains are trained to see motion. That's what that's really looking for. Depth perception, and we're going to get into this a little bit with like constancy, is this idea that, so I'll come back to that, that we see things, and our brain is meant, it receives the context of what is around us, and it tries to perceive in that way, oftentimes trying to control and recognize that things don't change. Right. So this can be tricked very easily by context. Right. The context clues in Ames' room is a famous example of that. It's like take a room and make it trapezoidal, so that like over here on this left side, it's a very normal sized room, but like the size of the room shrinks down on the right, and the cues around you look much smaller. Right. Like the roof slants down, the floor comes up. And our brains, again, how many times have you been in a room that's shaped like this? Probably never. So our brain can't understand it. It doesn't recognize it because we've never seen anything like that before. Our brain wants to save energy. It doesn't want to like blast through and be bottom up processing at all times. And so it top down processes with rooms are square, or rooms have like a constant shape. The floor is flat, the roof is flat, and people don't like change size. They're like whatever. If you're a couple of feet under the roof, then that's like how tall you are to some degree. So this Ames room, things that can mess that up. So what's happening is this perceptual constancy, right? Like you look at these, what shape is this door, right? It's a rectangle, but like it's a trapezoid, right? If you bottom up process, don't recognize it as a door, but we see like this line on the right is longer than this line. These are not straight. They are like, crooked, showing us a trapezoidal figure, and yet our brain never thinks of it like that. Our brain, you're never going to walk into a room and see an open door and be like, why is that door a trapezoid? You automatically recognize it as a rectangle. And our brain does all kinds of funky things like this. It does it automatically. It quickly processes all this pieces of information. This is often a good thing, but this perceptual constancy often gets in the way. This the blue, black, white, gold dress is a great example of this. We take the context clues of what's around us, and we think of it as one way or the other based on its surroundings. The dress was blue and black, but for the like 30-40% of people that saw it as white and gold, they were likely seeing the context clues around them, and their brain was telling them the story of what the color was. It wasn't allowing it to like change. So we basically, like when we see a color, if the lights change, right, if it gets darker or much lighter in the room, we recognize that light is the same, right? We recognize the color as the same. Our brain sees it as a color and then anchors that and says, this is what color that thing is. And then even when things change, we know it is that. That's what it is. And so, but if we see in different lightings, right, we're trying to adjust it in those lightings. Right? And so once you recognize something, it's hard to kind of change it around. So as an example, look at this light or look at this board, right? This is going to really mess with you. And if you don't believe me, look it up, or like get on here, print this out and mess around with it to see if it's right. But like A and B, you're looking at these, like they're the same color. I know it's hard to believe, but A and B are exactly the same color, right? So let me show you an example, right? Your brain, now look at B and A, B in this one, right? This may mess with you, but like look at B in this one. This right here, these two are the same. Now we'll go back to the original. These two are still like, see, B and A are the exact same color. I know it's hard to believe, but what's happening there is we've got this shadow on B, and so our brain is telling us, It's telling us that like we've got to keep this constant even in this light. So what's actually happening is this one's well lit. Our brain adjusts automatically based on the context clues of well lit versus shadowed, and then tells us a story and then kind of like reshapes it, perceives it differently. So the context clues explains why these are the same, but we see them as completely different. Yeah, the only reason that you can do this here is because you draw this line in between them to see them as the same. Okay, so context effects, that's like the moon, why we see that differently, stuff like that. And finally, perceptual adaptation. We change, we evolve. Our brains are able to grow pretty quickly to adjust to whatever changes. In children, we do have this critical period where we are developing our vision and our perception. So if you were to put like blinders on. I think they did this with kittens. They like put blinders on them for a couple weeks in their first years of life, and then they basically lived the rest of their life as if they had cataracts. Everything was blurry. They had much more rod development and less cone development. They like couldn't they like could see things, but they didn't have a lot of detail. Right? They had very little to no detail whatsoever. But as adults, once we've fully developed our vision, we make it through that critical period, we will adapt pretty quickly. So a best example, Stratton, psychologist, wore the goggles we wore for our carnival. You put the funky goggles on and you couldn't roll the ball or shoot the basket. You were always like 40% to the left. He wore inversion goggles. So literally this hilarious looking helmet that like locked off his eyes and made his vision upside down, right? Some sweet, these goggles. Put goggles upside down. And he did it for 8 full days, right? He would be nauseated for the first couple of days, felt sick, felt gross. But by day 6, fully adapted. He could do everything totally normal. He was walking around, shaking hands, talking to people, cooking food. Like everything was completely normal. 6 days. So he lived 2 days totally normal. By day 8, he was like, I've got this. I've totally adapted. Now let's see what we change it. Takes the goggles off, has the same experience. Takes him about 5 or 6 days again to reinvert his vision and get back to. So we will adjust to whatever vision changes for us, right? So if it skews or anything like that, we adjust, we adapt in some way. So that's 9.2b.